It's being recorded.
All right, cool.
All right.
Okay, so the title of the paper, I also forgot to write down the author's name, so forgive me for that, is Tensor Networks in a Nutshell. The archive link is on the spreadsheet. And that should be just high enough that I don't have to erase it from too short. All right, so what are tensor networks and why do we care about them? So tensor networks are basically just a way to draw out math on vectors, matrices, tensors. Vectors and matrices are both types of tensors, so that's a bit redundant, but in general, just sort of a way to draw out your algebra. For our concern, quantum circuits are a subset of tensor networks, so learning how the structure of these work is really useful for us because it can help you interpret quantum circuits in other ways. And also Feynman diagrams, fun fact, are also related to this. So it's all built into this kind of structure. So I'm just going to kind of go through, I think, about the first 3 sections. It's like it's about 34-page paper. So most of it's going to be examples, which I think is the best way to learn about something like this. But first, I have to tell you how you actually draw these things. So the first step is for each tensor, draw a symbol. So for each tensor, draw a symbol. Okay, so technically speaking, you can draw any symbol you want. We're going to adopt a sort of shorthand here where triangles like this might be a vector. So sometimes you'll see me write it like this, where you're reading it from right to left. But often they're drawn this way, where you read them top down. Okay. You might also label.
So if you write it that way on the left, is that cat? Like the directly with quantum circuits.
Yeah. So this is a
Left to right.
This
but
is
the
a
math
cat.
is right to left. Is it like that?
Yeah,
Okay.
it's a cat here. And a bra is exactly what you'd expect it to be.
Okay.
Sometimes they put a little bar. Just to be clear.
Yeah.
So, and it does matter. I'll write the. I already messed that up. All right, so I'll write the bra here. So it actually does matter the orientation because when you write them down, you can use abstract notation, algebraic notation, and you keep track of whether an index is upper or lower the whole time. So for this, I would write psi I, and this would be psi bar I lower. And again, that should be familiar if you've ever seen like GR or any sort of relativity where you're using Einstein notation. It's very similar to that. I actually kind of like this, and as we'll see later, it helps you get around a lot of the issues with writing things down in order. So if you're trying to trace back a circuit and you're worried about putting things in the right order, we'll see that this can actually help clean things up. So this would be a vector. It has one input at the top, or
Particularly
output, yeah. This is what the notes are for. Right. So this one's an output, this one's an input, and you just keep track of them from raised from lower index.
Sorry.
Yeah.
So when you say output input, you mean that the line is the input and the bundle is the output?
Yes. So the line here, the wire, is the input, and this one is the output.
Okay, I see.
Okay. For a matrix, so you might have a matrix A, like this, and then you would write that Aij, and that's equivalent to this sort of sideways thing. Like
I have
that.
a question.
Mhm.
We can write quantum circuits in this language, right?
Mhm.
So like with quantum circuits, time goes from left to right.
Yeah.
So we go vertical, is time going from bottom to top? Or is it the other way?
Yeah. Yes, this is the output.
Okay.
Right.
Okay. So
So-
time goes from bottom to top.
Right.
Good.
Okay, so this is a vector. This is a matrix. But more generally, you can write any sort of tensor, T. And sometimes for a matrix, we'll use a box and we'll use some diamonds or something else for a tensor. But in general, you can tell because it's just going to have some arbitrary number of inputs and outputs. So you might have A, B, C, and this is A, B, C, like that. We tend to write a raised index first. I think that's just a convention. And this is just a general tensor. And as you can see, this is more general than what we would use in a quantum circuit, because in a quantum circuit, you typically restrict that your number of inputs and outputs must match, so it's reversible.
I write the raised ones first because the order of the math will go from right to left, and so like match properly.
You can actually be pretty sloppy, I think, with the order when you write it down, because what you do, and I'm gonna go over this, is you just sort of match indices, and then you don't necessarily need to go to the algebraic form. You can just simplify the diagrams to do your math. So what matters in the diagrams is identifying edges. So like this wire will always be wire A, and that's what matters. And it matters that it's a output wire to C. Okay. All right. So this is step one. This is how to draw. Step two is juxtaposition. So that's a vocabulary word for the day, which is just where you have two or more tensors next to each other. Okay, so
It's like a GRE word, right? Juxtapose.
yeah, it's a great word to pepper into everyday conversation.
It doesn't have the R.
Oh, there's no R, yeah.
I'm bad at spelling.
That would be a new word.
Juxtapose is the new word. But so juxtaposition is you just put two tensors next to each other. And here we're only caring about unconnected tensors. So again, this is a pretty familiar thing. I think if you've ever looked at a quantum circuit. So it just says if you have two tensors next to each other, like this, you can describe their total system by tensor product. So we would write A tensor B, right? I'm leaving off indices here. You should be familiar with this. And just then basically you can slide it on their wires, and that's fine. And you can switch the wires. So you could do B, A, and this is equivalent, although not necessarily equal, because like you can think of these as Hilbert spaces. You can just swap your Hilbert spaces around, but they're still only acting on their own wires. Okay. And then, again, you can slide them. So you might have something like this. And that's equivalent to the other way around. Like that. And you can just think of this as B tensor I here, and then I tensor A, and then you simplify, you get here, same thing over here. So all of those are equivalent. Another interesting thing is that you can cross wires. So they always need to end up in the correct place, but in general, you can let them cross over each other as long as you maintain their endpoints. So like I can't pull this guy over here and shoot him up over here. Let me just draw what I mean. So you have something that looks like R, and we'll put that guy in a circle. And here, square. R has two inputs, one output. It goes like that. And then Q has something that does this, one input, and then three outputs. It goes like this. Okay. We can rearrange this. And formally, you say this that wires can cross tensor symbols. So I'm going to identify our edges here, just so we don't get mixed up. And remember, this guy is over here. So I mislabeling. Yeah, okay. So this guy over here, it's the same wire all the way through. And then you can think of picking this one up, popping it down over here so that it's closer to its input. D. And then shooting D and E off the right edge. And then just plopping R over here. And essentially swapping the order of these two, like so. And when you do that, you have to maintain that this is A, and that looks like an E, C. And then over here is F, and I'm missing G, so G needs to come over. So these two are the same. So that was a lot of just redrawing, just to say like crossings are things you can undo. You can think about picking up wires and moving them, fitting them to your heart's content. And you can also notice here, fun fact, you have R and Q reversing, right? So in a sense, it almost looks like they commute. So you have this sort of unconnected diagrams you can switch them back and forth, which again is something we would expect from the quantum circuits, right? Because they're acting on different Hilbert spaces if you think about those circuits. Okay. Do you want me to keep writing on this for you?
That's fine. We can switch over your mic.
Okay. All right, so now we know how to write tensors that are unconnected to each other. The next step is just to connect wires. All right, so connecting wires basically means that you contract the indices that the wires make. So graphically, what does that look like? So say I have a tensor A acting on a vector, like so, and I'm going to label these wires. So how I would write that algebraically, that's AI raised, and then here. All right, so Einstein notation says you just sum over the contracted indices. And then what that looks like is you can think about basically shorting that wire. So moving this guy down into here, and that's going to give you some resultant vector, call it psi on I. So this is going to be equal to psi I, like that. Okay, so that makes sense. We're pretty familiar with that. The other case, I think it can look a bit more complicated when you're dealing with higher order tensors. So let's see, we have something that looks like gamma. What did I call the other one? Delta. It doesn't really matter, but my own sanity. And say we have two shorted indices like this. So
This is now independent of the diagram at the top, right?
yeah, this is different. This is A, this is B examples. So first thing I would do is go through and label. Each wire gets only one label for, consistency. And then you just write this down. You can start the bottom to top, top to bottom. It doesn't really matter because you care about the indices and their relative raising and lowering. So it might be tempting too when you do this, because this is quantum computing, not GR. It might be tempting to just like let your labels fly up and down. Don't do that. It actually doesn't matter whether things are raised or lowered. Yeah, so when you do this, you get something like that.
I guess it's nice when sign goes from bottom to top, that tells you, like, you see A is above the M.
Yeah.
Right, yeah, so the indices are telling you the order. So, I can transpose these, you're still like summing them the same way. And when you do this, you can see there's only these two indices that aren't summed over. Let's call this tau AB. So I can say this is now equivalent to something like that. right? Just collapsing all the spaces where the wires are
Previously,
connected.
you were choosing squares, now you're choosing circles. Is there any significance to that?
Nope.
All right.
Yeah, like I said, you can pick any symbol you want. Typically, if you're gonna do something weird, we're gonna do it on this guy. The matrix tends to be a square, and we like the triangle for the vector. I think because there's a clear one-sidedness to it. But
Margaret, if I may ask kind of a weird question. So can you think of an example where the having the indices higher or lower would actually matter?
yes. So there's actually a quote at one point in the paper is like, okay, from this point on, whether or not the indices are raised or lowered matters. I think that's when it comes to when you're actually using this to evaluate diagrams. Specifically, this is sort of a precursor, hopefully I get to it, when you care about cups and caps. So you're gonna have the situation where something is like this, right? This is on a wire versus if
We're
you-
now going left to right, right? You switched like the weird time.
yeah, so you kind of switched it. So this is equivalent to A transpose when you take it around the wire. I haven't quite gotten to why that is yet, but this sort of wire formation of why it matters.
Basically, transpose is like time reversal, right?
Right. Yeah,
Or
you're flipping the indices.
you can think from matrix point of view, right? If you can multiply 4 cross 2 with 2 cross 1.
Yes.
But if you change the indices, let's say for the first one, it becomes 2 cross 4. Then you can no longer multiply
2 cross 4
with 2 cross 1. So
Yeah, so
no,
I that kind of is taken care of in the resultant indices though. So you always assume like your indices are gonna contract, right?
yeah,
So,
but I think if you change from up and down, that means changing the
The resultant
Yeah.
size, yeah. Is that true? I feel like here it's not because the resultant size is determined by the indices you're not contracting over. Like,
like the multiplication will not be possible if the indices are changed.
yeah,
If you change from up and down.
yeah, I think so.
I was
We
thinking
have
it
to
would-
proceed, sorry.
Yeah, we can check it.
Okay.
Because it's like half, you know, it's like 30 minutes.
Yeah.
All right. So where was I? All right, and so now we get to define what a tensor network is. I'll save time by not writing it down. But a tensor network is just some network where there are 2 or more tensors that are connected. Okay? Spoiler alert, wires count as tensors. So you can technically have a tensor network, it's just one symbol and wires. And we say a tensor network is fully connected. When all wires, when all wires, or they call them legs, so say all legs and arms. So pick your favorite term for whoever one are connected. And the tensor evaluates to a number. And in general, that number, I don't know, X can be contained in.
That's kind of weird. Wouldn't that mean that you would, for the vector, for example, psi, that would not qualify as a fully connected one?
It would not, no,
Interesting. Okay.
yeah, because it still has a tensor in it, yeah.
Yes. Okay. I see.
But you could consider, there are ways to make it into a fully connected tensor just by drawing more wires. All right, so now the question is the next step, number 4, is connection to Coleman, all right? And this is, I wrote it down in my notes and just for number keeping I'm gonna write it down here, but it's essentially just a statement that says, when we're in quantum computing, we write out our tensors in terms of computational basis. So you have some computational basis, okay? Right, because you want to feel like real computer scientists. And for all of your tensors T, so for all tensors T, you can write T as a sum of coefficients now. So here we're kind of referring to the whole thing using Einstein notation. Here you're referring to your coefficients. You still maintain the raising and lowering, and you'll see why. We use them to refer to both your vector space, but also your dual space. So now your lowering of your coefficient indicates that corresponds to your dual space versus your vector space. Cool.
So in this case, T in the sum, T, I, J, K are numbers.
Yeah, they're your indices.
No, I mean,
Yeah, PIJK numbers, yeah.
They correspond to your computational basis.
I'm gonna criticize your signal, sorry.
Where's my signal?
I thought it was an
It
epsilon.
looks like an epsilon.
Yep.
See?
Where's
Yep.
my signal?
the sum.
You have a signal. right?
Where's my signal?
There.
That's the proof.
You know what? All right. I accept that criticism
All right.
because
Because you couldn't find
obviously I was like,
it. Right.
I was looking for that.
Uh-huh.
So where did I write a signal?
And technically, okay, that's much nicer. It's gonna be like the little lanes and stuff.
All right. Obviously not an
Full
effort.
circle.
We have the same thing.
There's like a thing going on where people are writing signals with epsilon. You really can't find it.
I would disagree, but I can't. Okay. So again, we're noticed. You can double check me here if you want to. That your raise and your lowers are still consistent with the definition I used previously, wherein your raise are your outputs, right? So you can consider an input to T. You might call that some psi, and that would go over here, and that would be contracted with your input indices. Okay, so that all works out really nicely, and then psi would be written with output indices. All works out. Very consistent, very nice. Sorry to make you switch the camera.
Oh, thank you.
Okay. All right, so now we get to the main part, which is examples, and you might have thought we were doing examples the whole time, which we were, but this is specific examples of tensor networks that you might be interested in. So the first one is the epsilon tensor. And so it is meant to be an epsilon. The epsilon tensor. So this is, all right, I'm gonna confess I've never said this word out loud before. The Levi-Civita symbol?
Civita.
A little bit Civita.
Civita?
Yeah.
Okay, I've never said it before out loud. I just always kind of nod when everyone else does. All right, so that symbol can be used to calculate a determinant. So for example, in 2D.
Okay.
In 2D,
In 2D.
2D, I'm sorry.
So in 2D, it's given like this. So if you have some matrix S that you want to calculate the determinant of, you use the symbol, and then that's just given by this. J1, right? What else do I have, please? Yeah. So this is in 2D. It does generalize the higher orders. No? So
What is the 0 and what? Those are.
those are the because this is a 1-1 tensor.
The matrix.
Yeah.
Yeah, okay.
And it's 2D. So
I'm missing why we put 0 on the bottom. Am I missing something?
Okay, so,
Is it obvious to everyone?
I don't see it either, to be honest.
Is it like referring to particular column?
yeah. And so,
Is it a 2x2 matrix?
well, because each of these needs, yeah, it's in 2 feet. So it's a 1-1 tensor, so it's a 2x2 matrix.
Oh, okay. All right. So it's something special for 2x2 matrices.
Right.
All right.
Um,
That helps. I thought it was meant to be like a general.
not 2D.
Okay.
So, Margaret, if I'm understanding correctly, when you remove the 0 and the 1, you replace them with arbitrary indices, that's not the determinant. Right?
No,
You have
like
to
you
have
have
a
to, you have to add more terms.
I see.
Okay, now you say that tensor will be that.
Yes.
I see.
With CH or?
Yeah, there's like a
CIE.
silent, yeah,
Oh.
you have to, when you say it, you're supposed to say CH.
Okay.
Like the bread, ciabatta.
Like, yeah, like the bird.
Okay. All right.
It's
Um,
probably newer, yeah.
So I'm gonna draw this now. All right. So what this looks like is I have S here, and it goes into my epsilon tensor, and goes into S again, because S appears twice here. And you notice I'm not worrying about the order they're going in. I'm putting epsilon in the middle, because what matters is that these are contracted. So that's I, and that's J. And so whenever you see something like this, so a 2D epsilon tensor, since you know it evaluates this, you can write this out as just det S times your epsilon tensor. And you took your S's off of here. So this is the diagram that results from using this fact. So you can now,
A scalar times the
Yeah.
epsilon.
yeah, so scalars don't get symbols because they're not tensors, right? So they just kind of float around your diagram. But yeah, so you can write this back.
Wouldn't you just write down the determinant without that epsilon tensor though?
It's not equivalent to here because like again, you still have these legs. Commands is not fully evaluating. I think also this is more general than this because it says 0 and 1 versus this says that EIJ through SIM SJN is equal to epsilon and N times determinant of S. Is that absolute value?
Oh, I see.
So to be clear that that's not a tensor,
Yeah.
but
Oh, that.
yeah. So you're using this fact to write these down, but this is slightly more general that has zeros and ones versus this guy has, you know, in here. And so you have to preserve the fact that those lines are there.
Right.
They haven't been contracted. Okay, I already observed one observation. Okay, something else you can observe here. So I observed how you can kind of mess with the order a little bit. That's fine. But this is something like a quantum state. This is equivalent to the 2-qubit state given by
1001.
1/2, when we write now epsilon state is equal to 1/2, and then correct order minus incorrect order by the Logicivita logic. So this guy is now quantum state. And you can, yeah, that takes a bit of looking at, right?
I thought epsilon was a matrix, right?
Right. So again, we're gonna
No, but it's
foreshadow.
got 2 bottom indices, so it's like.
So you can also like zoom into the future here, and I can pull these wires out, put this guy to the end, and make it look like. Just pretend that that's only a straight line.
Right.
Yeah. Make it look like a vector with 2 outputs, a vector on 2 qubits.
All right, so is this where like you're flipping the cat to a bra. Like,
Oh, okay, yeah, thank you for that. Hold on. Yeah, so
okay, let me.
this is how, yeah, this is how it was drawn. Technically speaking, I think this one you cancel it, if nothing happens, just here and here. Because this is would be a bra, right?
Uh-huh.
But,
Okay, so like,
Yeah.
we're kind of, when we went to this diagram, everything before was bottom to top.
Mhm.
So it's consistent. But now here, we like flipped to going from left to right and then down to, I don't know.
right,
So I
so,
got a little confused. And then
Yeah.
like, before we had said, oh, if the index is above, then it's raised, and if it's below, it's lower. But then we violated that here. Right?
mhm. Okay, so first a note on this notation, the flipping is used by some authors, but not this one,
Okay,
so that's why they put the bar.
the bar.
The
Like,
bar.
oh, okay,
To indicate a cat. So here, they don't say, oh, you flipped it, now it's a.
oh, the bar
individual space.
indicates a bra, right?
Right.
So
I misspoke, yeah, and so over here. You could argue both of these. Should be like this. This is,
Oh.
yeah, I'm
Right.
drawing straight from, I
Hmm.
copied this drawing straight from their works with
Okay.
a criticism on the author.
right.
But yeah, for consistency's sake, just kind of flip this whole thing around, you
Okay.
know? But it works out to be such that you can write your epsilon tensor. You can move it into such a space as you can use it to define a quantum state on 2 qubits.
Okay.
We're going to use that later. So this is the first example of it kind of being relevant for quantum computing.
So Margot, I got everything you said except for the quantum state. So
Okay.
in terms of figure, I get what's happening,
Mhm.
but like if we're not speaking in terms of figures, what's exactly the operation that's bringing it to the quantum state?
Okay, so
Like I want to
That's
understand the
a-
mathematical analogy for that bringing the
Right.
wires together.
so that's a good question.
I mean, isn't it as simple as
It's
something
just-
with only bottom indices or only top indices is a vector?
Right.
That's pretty much it.
Yeah, that's basically it.
Sorry, could you repeat that?
Like anything with just bottom indices is a vector,
Mhm.
and anything with just top indices is also like the
Zool.
Dual vector, yeah. So technically, I mean, this is a dual, but they go ahead and define it this way. So technically, this is the drawing for the dual, I think, because this one ends up with quantum vectors. And that's your dual space. But without loss of generality, you can define a vector epsilon and here such that basically I've raised these two and epsilon is defined this way. But if you put it in a larger tensor network, it has this property where if the same matrix appears on either side, it contracts and it picks up a.
Okay, I see. It's
Yeah.
clear now. Okay.
Also important to note about this determinant is it's a global factor that's picked up in this case, so we don't care about it. In the terms of quantum computing, it doesn't affect anything.
No, wait, we don't care about global phase.
Yeah, but if it's a global
is
phase
a-
factor like here,
That's not a phase. It's not like an e to the I5. It's a number, right?
yeah, but because if you assume this is a unitary, it's gonna be magnitude 1.
Oh, all right.
Yeah, only for unitary that statement is.
Well, yeah, so most quantum circuits you're
Especially-
dealing with, that's unitary. So
And not all units are to that property, right?
magnitude 1.
Magnitude.
If it's equal to 1, they're a special unitary.
Okay, all right.
Okay,
Clear enough.
all right, so let's do another example, which is concurrence. Concurrence and entanglement.
Are you there, Lisa? Okay. She's asking about entanglement.
Oh, So this is one of them.
I heard a rustle.
Sometimes it's almost like I can hear them. Okay, so we're gonna let psi, and I apologize for my handwriting, be a 2-qubit state. Okay. Its concurrence is given by C of psi equal to absolute value of C prime of psi. And what is C prime, you may ask? It's this network, this fully connected network where I'm following my own advice and just drawing my symbols first. I don't know why I have such a hard time drawing triangles as an aside. I just kind of do. Okay, so this. So essentially, you can write down what this is if you want to. And I think that might be clear because we're more used to looking at algebraic notions. So this is epsilon ji epsilon ok, right?
So now we're thinking of the epsilon as a matrix, right? Where we take what the vector that you wrote and we flip one of the kets to a bra, right? And it becomes like a sigma y. Which is phase. Is that what I'm saying? Is that what I'm saying?
No, you kind of spoke quickly.
Okay. So like, do that here. So you wrote this.
Mhm.
Right, so now, if I flip this to a bra.
Mhm.
becomes a- That's a sigma y. So
Okay.
this is a matrix, right?
Yes. Mhm. And then so AI psi should both be on the same side. So JI JL.
Yep.
Yeah.
Yep.
Okay. Yes, and that all matches up because these are inputs, these are outputs. All right, so we're good. So this sort of thing. This is Cypher. And again, I like to pull the epsilon out of the cut. But you evaluate this. This is fully connected. So this just evaluates to a number, psi prime. Psi prime, that is a C prime. And this is an entanglement measure that you could use, for example, in finding their Smith decomposition for some state. So another cool thing you can check here is you can see what happens if you act with local unitaries on it, right? Because you would hope local unitaries shouldn't be able to affect either global entanglement between these two, right? So you're going to act with unitary U. So that is, make sure I get my daggers correct. Okay. So U1 over here on epsilon and then U1 dagger. And then you can do the same thing over here, doesn't matter. Right. And we already know what this guy does to be unitary. It just contracts this, so you would have your determinant, the magnitude of your determinant of U1, and then the magnitude of your determinant of U2, which are just, phase factors here and here. And they're magnitude 1. So the concurrence, whenever you contract the whole thing, won't vary with local unitaries, which is good. Good entanglement measure.
Sorry about it. Is the right one supposed to be U1 and the left is U1 dagger?
Either way.
Yeah, I think it
I
doesn't
mean,
matter.
either way is right, but
Yeah.
the idea is that the ket is, the right one's the bra.
Cool. Okay, so this is also a square. So,
No, I'm
okay.
talking about psi. So that the psi at the right extreme, right?
Mhm.
That's a ket.
Okay, so generally speaking, uh, unless I draw a bar,
Wow.
it's not necessarily, yeah. So it should be a ket because,
Like a
This
pawn
one should be a
circuit
ket.
goes from left to right.
yeah.
And the math goes from right to
Right. So this is a ket because all of its input, it only has inputs, it doesn't have an output. So that one, this one's a bra, this one's a ket.
Did you follow what I'm saying?
Didn't
You
you
got
say
a
the
pawn
opposite?
circuit.
Right.
I said the
time goes from
opposite,
left to
that's
right.
why I wrote the words.
Right, so like if I had U1, then U2, like suppose the
So
input
beautiful.
was
Yeah,
side,
that makes sense.
U1, U2. When I draw a circuit, I go U1, U2, U3. Time goes from left to right. But then when I write the math,
So in this one, time goes from left to right.
Um,
left to right or up to down. And in some, it seems like in some cases, doing all
Yeah.
kinds of things.
I think things are definitely made more difficult by the fact the author doesn't want to use the fact that if you flip it, it's the speed tool. But in general, what you can always refer to, because I keep accidentally mixing up the words, so I wrote them here. If they're lowered, they're in the dual space. So that means they're bra. They're raised, they're ket. Okay. And this is the bra. So I think that's how the dagger go.
Do a question.
Can I ask? Yeah. Before, when you had the determinant, you had S and S, and here you have U and U dagger.
Mhm.
So that's because of what you said before with the upper and lower lines. When you had the upper line, it was A. When you had the lower line, it was A dagger, something like that.
Yes. So then,
Okay.
like that's the cup thing.
Okay.
Um,
That's. Thank you.
which it's yeah. I have how much time do I have?
Well, that's negotiable.
Oh, okay. Well, I'm just gonna keep doing examples then. And so I'm gonna stay over here, like you're like a little easier.
How much more time would you like to have?
Well,
We started like 5 minutes late.
okay. Well, I'm on page 4 of I think the 10. So
All
Yeah,
right.
we should definitely discuss quantum circuits. If we're going to discuss that.
yeah. So I don't want to get too many examples at this level if it means I won't get to like bending and crossing wires, but I think we'll probably be good.
I would say like go until what 1:15. The clock is an hour. But sorry, it is right.
Now it's right.
2:15 I think would be 2:10 or 2:15 would be fine.
Okay. All right then. I'll draw this thing as a for you example. So this is your turn. Right. Have fun evaluating this. This is basically, so we saw you can use your epsilon tensor for entanglement measures. But it doesn't have to just be, you know, like the concurrence where it's only on a 2-qubit state. For instance, you could try to calculate the 3 tangle. Feel free to ask your parents what that is. Your
So,
physics
like,
parents.
okay, let me step in. So I know that concurrence is very popular, but like I was always like not very convinced how interesting this is because it's only for 2 qubits, right? So,
Right.
like, so what? I mean, like an entanglement measure, it's like somehow only interesting if it's. And then isn't it only for pure states? We do like a convex loop or something.
I guess, yeah, because you are assuming your state.
Yeah. So I don't know. I mean, it's nice that you can draw this diagram, but like I don't know if there's a generalization of concurrence that works beyond 2 qubits.
Well, maybe.
I mean, now you're going to show us
The
something.
3 tangle better.
I have heard of the 3 tangle also, but I never used it. So it's also another kind of limited entanglement measure, right? Is it only for qubits?
It says qubits, so.
No, it looks like quite a tangle, right?
Yeah, it does. It does look like a tangle, and so your turn. Write this out. You can do that I think that's a fun exercise to kind of get used to, like writing out all the indices.
Can you write 3 tangle and I'll take a picture?
You have in purpose only 5 epsilons and not 6 epsilons.
Thank you.
Gee, thanks, Margaret.
No, right?
I'm just gonna take a picture. You can be in it or not. it's your choice.
I never want to get a picture.
Never in any picture.
I prefer not to be. Okay, so this thing is,
We need you in the group picture.
Yeah, we need you in the group picture.
all right, so your free tangle is given by 2 times this guy of size.
So the point is there's no way to contract this into a simpler form.
This is, to me, this looks pretty simple. This is pretty simple. You can write it out. It's just epsilons and 5. This one should have a bar.
Let's see.
So this is the example, and I have my answer to it if you want to check later.
And
But
the only one you connect to the left is the bottom one.
yeah, that's the one that makes it a little bit more fun.
Okay, so there's a natural question like, what if you were to repeat this an integer number of times, right?
Mhm.
You get an interesting measure of whatever that anyone would care
I don't know. Yeah, but that's maybe interesting to look at. And I think definitely easier to think of repeating this onward in this format
Okay.
versus like if you were just looking at algebraic equations.
about. This is only for qubits, right?
It looks like it,
Because the
yes.
epsilon is there.
Um,
And so far, we've only defined it. for
this does look, so at some point we are gonna have density matrices, assuming I get to them. I have a privilege purification backwards.
Okay,
But yeah, this is a little bit deceiving right here because it looks like a row, right? It looks like
Okay.
a row, but they're pure states. So
what were these little brackets you put in? You're trying to complete the triangle?
I was just indicating here.
Oh, okay,
Look here.
all right,
All right. So
interesting diagram.
I also at one point I had an equation. I was like, oh, here, this is also their equation they gave you to try out yourself. But whenever I went to write it out, it was horrible looking. So I'm going to spare you all that pain. Feel free to look at the paper if you want to try it out yourself.
Can you move the camera, please?
Yeah.
So the paper is called Tensor Networks, I'm not sure.
Yes.
Right, okay.
And it's linked on the spreadsheet. All right. So
Didn't they make a book out of this?
it's a 34-page long paper. It's
Okay.
not short,
Mhm.
but it's a quick read.
Mhm.
So definitely, I'm kind of giving you the TLDR on the paper right now, but definitely look at it. It's very readable. All right, so
Sorry, is there any intuition why these are entangled measures? So like you can do the unitary trick and then it's invariant and you look at unitaries.
mhm. I
But
think
then like for a product state, is it clear it'll evaluate to like 0 or some lowest value?
I don't know. Yeah, that's probably a good question. I think the metric that keeps appearing in the entangled measures is that you're contracting psi with itself. So you're contracting your vector with itself, and you're getting some sort of self-correlation.
Mhm. What if we have a single qubit, we do a, cat and a bra with an epsilon between, what is that value? It's like sigma y on a qubit, right? It's like expectation of sigma
Yeah.
y,
Mhm.
right? So then that's something.
I'm gonna. Okay, so I wanted to do a quantum network, go over copy and XOR, and then we got wires.
Are we thinking of generalizing it now? Like.
I was just trying to understand it, like why it's an entangled measure.
So quantum circuits. So many of you will have seen this before. This is the quantum circuit for a Bell state, correct? This generates a Bell state. And I put my zeros and little triangles here to indicate that they are also tensors. And this is a tensor network. So you can also use this, identify edges. So E, this would be C, D, E. And you can use this to write out the action pattern. So you can say the action of the circuit. So you might say ket B, ket A. Why did I write it this way? Who knows? I like playing around with order. So yeah, okay. See? And so you can also write the action of this diagram this way. And at the end, you should get something that has,
That's very tricky.
yeah, so you can, don't necessarily suggest it, but you can, and you will get, as a result, some vector. I forget which one comes first. Yeah. We'll just erase them at the end, right? And you can look at their specific decompositions of these two in terms of this abstract algebra that make it clear that this is what you get. But just, I wanted to quickly nod at that before moving on for time's sake.
So would writing things down in this way give us any advantage in terms of, like, I don't know, maybe some insights that might be useful?
Yeah, so okay, I want to skip directly to purification and so you can use this for like entanglement topology. You can use this makes looking at SVD, so singular value decomposition, and how you use that, for instance, in the Schmidt decomposition and other networks. It makes it look a lot easier than, in my experience, looking directly at the algebra would. So this might not be helpful, but I think looking at things this way and realizing that they're tensor networks is helpful, particularly when you're looking at the wires, the funky things you can do with wires.
Like tangling them and stuff like that.
Yeah, tangling them, bending them, and using them to transpose things, and that kind of that foreshadowing trick where I turned epsilon into a vector, where you kind of, in this way, as we're going to see, and that's the very next section I wanted to do, you can exploit a sort of vector map duality that isn't super, I never thought of it that way in previous, algebraic approaches to quantum, but looking at the diagrams, it's super easy to do, just sliding it around the wire. Okay, so, real quick, also, I want to define copy. So copy, it looks like this. Input to the bottom, output to the top. Right? Yeah. Okay. Where basically it evaluates to 1 if all of the edges are the same, or it disappears elsewhere. So 0 if they're not. Why does that copy? Well, because if you put a 0 here, then you either get air, nothing, or you get a 0 here, a 0 here, both of those legs. So you can think of the way this guy works is it contracts the vector with this dot. It says now my outputs must be whatever my input was. And so you get a copy.
Right, but it only works in a basis, right?
Yeah. Well,
Otherwise, like the problems with no point, right?
yeah. So this
is
is
it like a C naught to a 0?
so C naught is a copy with an XOR. So the way you can kind of look at this, if you flatten those two outputs out, it looks like this. it's your control, right? But you can't just have a control floating by itself in quantum. You have to have something it's controlling.
Okay.
So it's sort of incomplete as far as quantum circuits are concerned, the quantum network diagrams are concerned, because they're a highly restricted subclass of tensor networks. So this is okay for a tensor network, but not for a quantum network. You have to have something it's controlling.
This behavior of copy is it's defined on 0 and 1 and then extended by linearity.
No, it's just define whatever vector you put in here. So you can have some sign here. And it pops it out over here,
So it's like a plot.
which is
So
why
just allow ourselves.
you can't use it actually in quantum.
You're not
Without-
allowed to use.
You're not allowed to use it by itself.
Okay.
So you can't just clone your state.
Yeah.
Your quantum circuit is more restricted than that.
Okay.
But you could attach something like an XOR, which looks like this.
Doesn't the psi is fixed and it's okay, right? To copy. There's no problem with that if psi is fixed.
Besides known,
Yes,
that's fine.
yes.
Yeah. But for a general copy,
Right.
you don't let yourself just use a copy. So XOR, you might see now if I erase these how the two connect, right? XOR is just you need an even number of unity at the output. So that is defined on the basis. So if you have 0 here, these either have to both be 0 or both be 1. And you can define 1/√2 XOR as equal to copy with a hand word on every arm. Like that. Or that XOR copies a plus or minus state. So XOR on plus gives you plus plus. And similarly on minus gives you minus minus. The C naught is the two of these contracted. Okay, and you can see how you do it. You literally just identify there. All right, that was my last example in that section. So I'm going to move on to part 2, which is bending wires. So bending wires and crossing wires. So the first thing on this part, I think I wrote down way more than what I'm capable of covering. So I'm just gonna write down how wires act. So they are a type of tensor. And so we define them this way. A straight wire is IJ. You have a cup, which is like this, which is both of them are raised. And you have a cap, which is like this, or both of them are lowered. And the most interesting part of this is that you can write them in terms of tensors. So this is a identity tensor, which you would kind of expect. It's plain wire. This one, however, is more interesting. The cup is IJ on IJ, right? Because they're both raised, so it's a cap. Some are all IJ. Well, this is just sum over K. K. That is an unnormalized max limit state.
Entangled.
Thank you. Entangled state. I don't know why I keep saying it. Yeah, it is unnormalized maximally entangled state. And you can imagine normalizing it. So, for example, if it was a 2D or whatever, or 2 somewhere by your diagram. Yeah, so this is the middle state, which is interesting. This is just the dual of the bell. The bell state.
So how can we clarify the dimensions of our system just by looking at the picture? Is there a way to see that?
So I think the dimensions, so that's an interesting question, and I think it's a bit convoluted. So, you know, you don't necessarily know the dimensions in these indices, like when you write a ket, you know, you have some phi, you know how many systems it's on, given by the number of lines, but not necessarily the dimensionality of it. And I think that that's also a bit true for quantum computing. You know how many, whenever you label it, you know how many systems it's on. But we know implicitly, you know, each qubit is 2, and then it tensors out. And again, so if you know each of the dimensionalities of each of the wires, you can tensor product them up to get your higher order dimensionality. But I think, yeah, that is kind of condensed in there, that you don't necessarily know how many i's and j's you need to consider.
And do we use these methods only for qubits, or can we generalize it, or has it been generalized for like any kind of system? So I know you haven't specified any system, but in terms of
a density matrix, for example, is just a tensor. It's just a tensor with special properties. So it's, you know, positive semi-definite, and like you have the fact that the diagonal sums to 1, but
Probably
That-
wrapped up in like 5.
okay, yeah, but suffice to say, you can put a density matrix in there. It just doesn't look like a vector. It looks like a tensor. Okay. Yeah, so you can observe really quickly, just you can double check that anything that snakes like that or snakes like this is just a straight line. That's pretty straightforward to see, and it makes sense topologically. You should just pull the line straight. You can also use this to do swaps. So like this, right? You can kind of convince yourself that you just interchange indices here. And of course, you notice you swap twice. That's just equivalent to straight wires. Okay. And then, right, using these 2 facts are how you get the transpose I did before. So I'm gonna try to go over this really quickly. We take a transpose of A. You put A on a wire and you just bend it around. And when you slide it around the wire, it transposes itself. And that's because of the cup cap identification this way. All right, really quickly, and we're going to run through partial trace and Penrose's and tangled pairs. So partial trace, you might imagine, and a full trace, you just take a matrix, so, or a tensor, A, and you identify each input with its output, like that, that's the trace. And then a partial trace, for example, over some sigma that's defined on multiple, you just only identify those pairs. Okay. So that would be, for example, if this is an A and this is a B, because B goes all the way around, you're tracing over that second subsystem there. Penrose used this to describe entangled states. And the way he did this is he had pure state where one of the systems is traced out. And then you can deform this, so you can think about unbending this wire here. Or rather, picking this guy and moving it around here. And you're allowed to do that because this is there's a cup and a cap here. So a little bit of imagination, they're making an S. You can flip it around, but your outputs still have to go where they were originally. And that's fine. So you end up something that looks like this. And then you have a new description of an entangled pair. So yeah, that one was really cool. I had to go back and reread that part to figure out how they were allowed to do that, but it's cup then cap. You can basically unbend them as long as these two go.
This is used in a quantum algorithm.
Is it?
Remember I was talking about singular value transform.
Yeah, so
And-
singular value transforms
Right,
was
so-
very
So, this is, I think it's gonna be different what you're talking about. So there's a question of, given a circuit to make a pure state, how do you make a unitary such that the top left corner is a density matrix corresponds to the reduction of the pure state. And I think this is the construction.
That would make sense because this is also used even just when they're doing SVDs, bending things around.
They have a whole section on SVDs, right?
They do, yeah. Maybe not as thorough as you would hope, but it kind of gives you a picture of it. But I thought this would be really interesting to look at. The
Yeah,
other,
and this is used also in quantum random walks. For this purpose.
the unbending.
To encode a density matrix in the top left corner.
Okay. All right. I don't think I have time to go over anything else then. Since it's like
Do
2:50.
you want to make a closing statement?
Sure. Read the paper. It's super readable. I think this is basically most of the paper is examples like I've been going over here. It takes a little bit of getting used to, I think, but it's an interesting computational tool to be able to look at things this way. And yeah, so if you're familiar, especially with topology, I think it's very intuitive as well.
Sorry, what exactly happened to show this equality?
Here.
Yeah,
Um,
so it's like, sorry, I think it's described into like the physical motion. Is it like you took this and put this down and like moved this up?
Mhm.
And this
yeah,
up?
you're
Right.
able to just pick them up and move them.
But more like you take the bottom one to the right.
Right
like
side,
that.
Yeah, so it's literally, it's traveling along the wire.
Oh,
Yeah.
that's very good. Interesting. I mean, I proved that mathematically. But I didn't.
And I mean, the transpose thing you use is what we call the transpose trick.
Mhm. Yeah, yeah. I knew that.
I think the whole sliding around the wire is really cool, and it's very intuitive if you know like some topology. I think
Mhm.
you're familiar with that deforming way of thinking about things.
Okay. What are the other things you would have told us about if you had more time?
So
Briefly.
briefly, okay. So using it to do complex conjugation, you can do a partial trace over the Bell states if you describe the Bell states that way, and see that you get a maximum mixed state. You just get a straight wire. Actually, it's pretty cool.
What with the scalar property?
Yeah. Well, here
Oh,
they're
no,
not.
you
They're
used
not
the
normalized.
unnormalized one.
Yeah, they're not normalized here.
I see.
And given a
Oh, I can see that you just draw it.
and given an abundance of time, and notes on SVDs and how you can use this to show purification of a density matrix.
Is that one
Yeah.
quick?
You do it backwards, so it's
All right. Maybe try to show us that one quickly. That's maybe-
okay. This has the least amount of reading on it. Okay, so this uses the SVD diagram, but just believe me, that it's in the paper and I didn't make it up myself. All right, so for all psi AV pure states, you can do a partial trace over them, like so, such that if you use the Schmidt decomposition, which you can read about is derived from SVDs, you can yield a positive semi-definite matrix. And what that is diagrammatically is this is dark box, dagger, this here indicates a diagonal matrix. And this is clear box. I wish I was making this up, but nope, this is in the paper. This is dark box on diagram. This is diagonal matrix and this is clear. These three are just given by your SPD of psi.
Oh. So is this, okay, you wrote, this is an equality, okay, with the loop, it's an equality. So SVD is from the Schmidt decomposition for psi. That's very nice.
SVD gives you the Schmidt decomposition.
Right, that's right.
Yeah. So, and this guy has all of your coefficients, your Schmidt coefficient. All right, so now that you've done this, you can imagine taking both the ends and just pulling it straight.
Oh,
Yeah, this guy has a dagger on it. It's gonna hit this guy. That goes
Yeah.
away. You're gonna get dark box, diamond, diamond,
Double done.
dark box.
Scheme level.
So what this is an eigenvalue decomposition of a square matrix, where these guys, it has eigenvalues given by the Schmidt coefficients of the original square, right? Fits.
Yeah.
Diagonal, and then this is just a new SVD decomposition. And so this is a density matrix. This is a mixed state. If you normalize it, so if psi is normalized, have fun reading upside down. This is a density matrix. And so the proof that you can purify any density matrix is that you can always write them this way. And then you can use this thing backwards.
Okay. Cool.
Yeah.
All right.
I vastly overestimated how much I could talk about.
Oh, well, we asked you a lot.
Yeah.
We stopped you a lot. So it's very nice and, yeah, I like that the agenda came out. You can see it graphically actually. You know, the three tangle, that's an amazing way to see it.
It looks tangled, but
Yeah.
it kind of isn't compared to some of the diagrams I drew for other equations.
Yeah.
That looks so neat. There's one part where he asked the reader, like, here's an equation, draw the diagram. And I did that and it was ugly. It was frankly horrendous.
Okay, you're gonna stop it.
So I know that Kunal is using this, but is anyone else using it? Are you thinking about using it, Margarite?
Now that I know about it, yeah. I like